Hello class, welcome back. What we're going to talk about today, or at the beginning of the video, is the reactions of ethers. Now this is interesting because ethers are relatively inert. They don't react with many things, and since they're relatively inert, we use them as solvents. But we can still get them to react if we force them. So just remember, ethers, they're solvents. But we can do some reactions with them. The book mentions two of them. I want to talk about just one of those. And that is when you take a ether, okay, and you treat it with some acid. And typically, excess amount of acid, you want a lot of it. And the type of acids that we're going to use is HX. HX, like so. Now, and we have to add some heat. So we've got to force this, because remember, ethers are relatively inert. Now the type of, excuse me, the type of acid that you need or will work is HBr, HI. Those two work the best. You can use hydrochloric acid, but it's inefficient. Yeah, so those two are the ones that we really want to use. And HF, hydrofluoric acid, doesn't work at all. All right. So just remember, HBr, HI, those are the acids that you're going to use to react your ether. And what you do, or what happens, let's designate this as, just put some designations right there. So what's going to happen, if you treated it with HBr, okay, what you're going to get is plus water to like that. So what are we making? We can take an ether and generate an alkyl halide. Pretty straightforward. Now, when I go through the mechanism, that will help us understand some limitations and or how the mechanism can change. Okay. So if we have let's do diethyl ether here, dimethyl ether, sorry. Right, like so. We can draw in our methyls if we'd want, but that's going to be a little cumbersome as I continue through this mechanism. So if we treat this with HX, the first step is, well, the only thing that has lone pairs is the oxygen. So the oxygen is going to abstract. Leave that open there. I'm going to represent it like this now. Not Br. I'm going to do X minus. There's our halogen right there. And then we'll just do a SN2 type style here, making sure we realize that there's 4 lone pairs. And maybe it's a little easier if we draw in our methyls. Like that. So this can come in like so, and then kick that off like that. And that's going to give us an alcohol plus our CH3X. So there's our first one. See how we actually generate 2? So what do you think the next step is? There's going to still be acid present, okay? Because we said there's excess acid. So we're going to do another protonation step. So we'll go like that. Now we have another good leaving group. But we have X minus now again. That one is right there. So that's going to come in and do another SN2. And then you can see that in that last step, what have we generated? Our water. So you can see that it matches right there. Okay. Now, what if you had a different type of ether? What if we had, let's say, if we had an ether like this. So the first step right here is going to be just fine. We'll generate that. But so along the way here, this molecule now looks like this. So we're going to, if we come here, we still are going to do the proton transfer here. Now, the mechanism is going to change slightly because what do we have here? Let's fix it up. So the mechanism will change now, like so. So why does the mechanism change when we have this tertiary alcohol? Because it's a tertiary alcohol. Can we do a SN2 style on a tertiary carbon? We can't. So the mechanism changes from an SN2 to a SN1. So it leaves first. And so we have water that is left plus let's draw it a little bit better, shall we? A tertiary carbocation. And then we have our X minus still floating around. And so you can see now it's more of a SN1 style in this second step. So that's going to come in like so to form our tertiary alkyl halide. All right. So the mechanism for the treating ethers with acid under excess acid and some heat can generate our alkyl halides. Okay. Let's see here. So that's the reaction that I want you to understand. So the next topic that we're going to discuss is the nomenclature of ethers. And we've already discussed that at the beginning of the semester, but now we're going to add to that. Okay? So at the beginning of the semester, we only talked about how to name ethers like so, that are linear. But now we're going to take a look at ethers that are cyclic. So we could have something that looks like this. See, these are cyclic ethers. You need to know how to name those now. We did not talk about naming these types of molecules at the beginning of the semester. So a little bit more nomenclature. So now when we take a look at the different types of ethers that are cyclic, they have different names. We have oxiranes when it's a 3-membered ring, oxytanes with 4, oxalanes with 5, and oxanes with 6. Okay. So you have these different types of names for these ethers. You should be able, I would like you to know those names because it's good to know. Now, am I going to have you, when we start adding like crazy other substituents to it, ask you to know how to name these types over here? No. Okay. All I want you to understand about the 4, 5, and 6-membered rings are those base names. Okay. Now, the 3-membered ring, we're going to understand a little bit more. So the oxiranes, they have another name. They're called epoxides. Okay. Now, epoxides are very relevant in nature, even though they have a 3-membered ring and they're very strained. Okay. So when you're comparing these ethers, this one right here would be the lowest in energy because it's a 6-membered ring. This has a lot of angle strain, so it's the most reactive. Just because it's the most reactive doesn't mean that it can't be somewhat stable. And it is, because we find it in nature all the time. So we have these epoxides. Okay? And the most simple epoxide is when you have these 2 carbons here, and all you have are hydrogens attached to those. And that just has a common name. So ethylene oxide, like that. So you separate the 2 words. So that right there is ethylene oxide. But when we start adding more complex groups to that epoxide, there's going to be 2 methods on how to systematically name these epoxides. So let's look at the first method right here. Let's see, marker here. So our first method right here is when, how can I put this here? When we take a look at this oxygen right here, that's going to be a substituent. So when we treat the oxygen as a substituent, okay? So for example, if we had an epoxide, maybe let's see if we get let's see if this marker looks good here. All right, so let's draw ourselves an epoxide, like so. And we have 2 methyl groups on that carbon. And then we have a ethyl group on that one, and an ethyl group on that one. Now, how do we know, in the first method, how do we name this molecule? Well, we just find the longest carbon chain, okay? And so we can see, if we number it this way, 1, 2, 3, 4, 5. And when we number it this way, we want to include the 2 carbons that are directly attached to the oxygen and find the longest carbon chain that way. So I've numbered it that way and see that there's 5 carbons long, right? But could I have numbered this in a different way to bump into, so when did we bump into our first substituent? When we numbered it this way, at carbon 3. So if I numbered it this way, 1, 2, 3, 4, 5. You see how I bump into the first substituent at carbon 2? And the substituents could be considered the oxygen or the methyl, right? So let's make sure we have that numbered the correct way. So then what is our parent? Well, we said 5 carbons long, right? So that would have to be a pentane. That's our parent name. So pentane. And where's our substituents here? Well, I see that we have a methyl group at carbon 2, a 2-methyl. I see we have a 3-ethyl, because here's our ethyl group. This ethyl is actually part of the parent chain, so we don't count it as a substituent. And then we see that at carbon 2 and at carbon 3, we're connected to an oxygen. And so that's a 2,3, that carbon 2 and carbon 3. That's where the double bond or the oxygen's located. And the way that we describe that is we call that right there, that epoxide, we call it an epoxy, like so. So this epoxide ring is treated as a substituent. And where is it in that longest carbon chain? So now all we have to do is take these substituents and just alphabetize them and spell out the name. So we have an E and an M. So E's come before M, that's for sure. And then we have to break the tie, E, E, T, P. So epoxy wins out because P comes before the T. So that would be 2,3 dash epoxy dash 3-ethyl dash 2-methyl. Oh, get our dash here. And then, so that accounts for all of the substituents. So now, what's our parent name? 1, 2, 3, 4, 5, pentane. So that's the first method for naming epoxides. Okay. So now let's take a look at doing the second method. Now in the second method, we use the epoxide as the parent. And when the epoxide is the parent, we use that name right there to say that's the parent name, okay? So oxiranes, so that right there is the parent. So we already found it. Parent, there it is. So the way that you number this here is number 1, number 2, number 3. All right. Now let's pay attention to this. Why could I not? You always number the oxygen as number 1. But why didn't I go 2, 3? Why did I not do it that way? Well, in this particular case, we have these 2 carbons right here. They both have 2 R groups. All right. So if we only had 1, well, let's just keep it right here for now. Now we have 2 R groups, so can we distinguish one over the other? No, well, now we have to take a closer look at the groups. And that's going to help us decide if we number this carbon 2 or carbon 3. And the way that you break this tie is you are treating the epoxide as the parent. And so that means all the substituents, everything else that's attached to the 3-membered ring are substituents. So at this carbon, I see that there's 2 methyls, right? So that's a 2,2-dimethyl. That's not how we spell it. Well, take away the numbers for a second here. So we have 2 methyls, and then we have a diethyl, right? Now this is how we know how to number it. Because everything else being equal, there's 2 substituents here, 2 substituents here. Now we just have to alphabetize it. And we can see that E comes before M. So E is going to take priority. So that's why we're going to get rid of these pink numbers here and number it in that fashion. So ethyls, E comes before M. So now that it's numbered, we see that would be a 2,2-diethyl. And then this one would be a 3,3-dimethyl. Okay? So now we just put the name together. So 2,2-diethyl is the first substituent. And then we have 3,3-dimethyl. There's the second set of substituents. And then what's the parent name? Oxiranes. Like that. Okay? So there's two methods to be aware of. And for me, on the exam, it doesn't matter to me. If it's a free response question, and I ask you to name this molecule, if you use method 1 or method 2, doesn't matter to me. It's the same thing. Potato, potato. Okay, so now what we want to do is how do we make epoxides? And you already know how to do this. That is, if you take an alkene, okay, and in this particular example, the R groups are cis to one another. And if we wanted to convert that into a epoxide, we would treat it with a peroxy acid. And a good peroxy acid that we're used to, that we've seen before, is MCPBA. Right there. Now remember, a peroxy acid has this general formula, like that. So a carboxylic acid, remember, looks like this. Carboxylic acid, peroxy acid. And MCPBA is just a named peroxy acid. Okay? Now, when we take MCPBA and treat it with an alkene, what are we going to generate? We are going to generate an epoxide. This marker is also dying on me. Going to generate, so this carbon, carbon 1, carbon 2, that's what I'm doing here. We form a ring, and then the substituents, the the stereochemistry of these R groups stay the same. So they're cis here, so that means that they have to be cis on the epoxide. Really straightforward concept. And that's a reaction that we've already seen. Okay? So that's one way to make epoxides. You've seen that already. Now, I just want to make sure you remember this. What if we switch those? How would our epoxide look now? Well, these two R groups right here are trans to one another. So we would have to switch those. Like that. So the stereochemistry is retained. Trans, trans. Now, we've also seen this type of reaction right here, where we can treat it with elemental bromine right here and treat it with water, right? And when we do that, we're going to have the bromine add and then the water or the hydroxyl add in an anti-fashion. Remember that? Remember what the name of this reaction is called? Let's see. Halohydrins. Because we have our halogen and we're adding our alcohol group there. Okay. Now, when we do this reaction, the halogen can approach from the top face of the molecule or the bottom face of the molecule. So because it has options of a top attack or bottom attack, we are going to generate an enantiomer. So these reactions you've seen before, this one goes from an alkene to an epoxide directly. This reaction gets us to the halohydrin. It's not an epoxide, but look at what can happen here. We could treat that in a second reaction. So this is reaction 1, and then in reaction 2, we can treat that with some sodium hydroxide right here, and that is going to form our epoxide. Like so. But let's take a look at that. So for right now, let's not worry about the stereochemistry. Let's just look at it that way. Okay. Now, when we take a look at the mechanism, I'll worry more about the stereochemistry. But you see what's happening? Alkene, halohydrin. Second, you treat it with the base, and you're going to form an epoxide. Can you see it in your mind's eye, the mechanism of what's going on? What's happening here? Well, if we take a look at the halohydrin, what do we have here? We have a bromine there. And on the opposite side of the ring, we have our hydroxide. Hydroxyl. Sorry, and it's not a hydroxide, it's a hydroxyl. When we add our sodium hydroxides act as bases, right? Strong base, that can come and abstract that proton like so. And that's going to give us our bromine is a wedged. Now our alkoxide is negatively charged. Can't see that very well, can we? Let's get rid of that pen as well. So now this alkoxide can act as a nucleophile. And it's going to attack in an SN2 fashion, but a intramolecular SN2 fashion. So these lone pairs here on this oxygen can attack, backside attack, kicking off the leaving group. So generally, you could say, okay, you form the epoxide, but what's the stereochemistry? Let's take a look at what's happening here mechanistically. This oxygen is on the bottom face, shown by the dashes, and it's going to come in backside attack. So it has to attack backside, right? So backside would be a dashed. Backside attack. This bond right here is already a dash. And so put our oxygen right there. SN2 is always backside attack. So could we, based off of the mechanism that I've shown you, could you form the epoxide when the alcohol is on the same side of the leaving group? It can't work because it can't do backside attack. Because when we take a look at this hydroxyl is on the top face of the ring. The hydroxyl's over here, right? And then what's also on top of the ring? The bromine. So it can't do backside attack because it's all up here. Okay, so make sure that that makes sense, and if it doesn't, let's chat and we can go over it in more detail. So one way to illustrate that, let's illustrate it with the mechanism, but by looking at it with chairs, maybe that will make more sense. Okay, so let's say our molecule looked like this. Let's say our molecule looked like this, okay? Let's convert that into a chair. Like that. Right there. Those are on opposite sides. Like so. Okay, so this is that. Now, when we add the sodium hydroxide, we're going to deprotonate that, turn that into the alkoxide, right? So this is on the top side of the ring, that's on the bottom side of the ring. And so mechanistically, we can see that this lone pair is going to stay on the top face and just come in from the back side. That's on the top face, the bromine's on the bottom face, and that's going to kick it off. All right. The hydroxyl, yeah. And so when we take a look at our product, if we draw it this way, this hydroxyl or alkoxide is on the top face. So we can say it's on the top face, like so. Okay. Or if you want to keep it in the chair, we could draw it something like this. So that oxygen right here, we could go like this. Like so. You see that it's above the ring. Okay. So when you want to make an epoxide going through the halohydrin, you just need to make sure that when you start with your alkene here, that you write it in step form. Step 1, you do that. And then step 2, you add the sodium hydroxide. And if you do it stepwise like that, then you are going to generate your epoxide. Okay? If you don't have it numerated, it's not going to work. It has to be numerated. Okay? Let's see here. Now, something that I want you to be aware of is this concept called enantioselective epoxidation. So we have enantioselective epoxidation. So what does that mean? Well, looking at the words and trying to understand what I'm talking about, just by looking at that title there, you can tell that we are going to make an epoxide, but we are going to select for one of the enantiomers. So for example, if you had a alkene that looks something like this. Let's draw another ethyl there. Isopropyl, something like that. When you did the epoxidation, what would you get? Let's do it with MCPBA. What would your product look like? You would have our ethyl there, and our methyl there, our oxygen. And so our ethyl right there, so that means our isopropyl is also on the same side, right? And our ethyl like that. Okay. But what are we going to get? Because this molecule right here, these carbons right here are sp2 hybridized. So that means the peroxy acid can come in from the top face or from the bottom face. So you are going to generate the enantiomer. So what's that enantiomer going to look like? So it just gets swapped here. It's a propyl. So that makes our ethyl there. Like so. Okay, so mirror images that are not superimposable. So those are enantiomers. And if you did this reaction, you would get a racemic mixture. Okay. So we get a racemic mixture because of the equal probability of the approach of the peroxy acid from the top or the bottom face. But there are some very smart people that can select for one of the enantiomers by using a special catalyst. And the organic synthesis, or the organic chemist who discovered this, was Barry Sharpless. And he discovered how to form an epoxide, but favoring only one of these. Now that's pretty powerful, because when we just use MCPBA, we get a 50-50 mix. And then trying to, if you only want one enantiomer, well, your yield has already been chopped in half because you have two enantiomers. And then it's going to be really difficult to separate your one enantiomer from this one. It's not impossible, it's just difficult. And when things are more difficult, it takes time and money. So if you could say, hey, I don't want this one, and if there's an easy way to do it, then that's amazing. So Barry Sharpless helps us to do the enantioselective epoxidation. So I want to show you those conditions just so you're aware of them. Okay. So in an enantioselective epoxidation, let's talk about the players. So you're going to have this titanium catalyst, and you can see that we have four isopropyl groups here that are attached to the alcohol here. So we have the titanium tetraisopropyl propoxide. Okay. So we have that piece. And then we have two choices. We could add a little bit of this guy right here, or a little bit of this guy. Now, when we take a look at these two structures right here, they're the same molecule. They're both diethyl tartrate. But one, we can see that the stereocenters here, they're different. Okay? And so we have the positive diethyl tartrate or the negative diethyl tartrate. Okay? So we have some of this. You pick which one you want. Okay? If you pick which one you want, so let's put that in our reaction conditions here. We could, let's just put in a positive DET. We can add this catalyst here. And so we can spell it out. And we could go, let's see, TI CH2 CH3, and there's two of them. Yeah. Okay, so that piece in the parentheses is this whole piece right there. And how many do we have of those? 4 of those. Okay, so we got a lot of reagents here. We have the titanium, we have the diethyl tartrate, and we need a peroxy acid. Okay, and so we have another reagent, and we have room here at the bottom here. And so we need the peroxy acid. So that would be OOH, and a common one right there. Okay, is that on the board just fine? Perfect. So here's our peroxy acid. That's analogous to adding our MCPBA. But now we're just adding these 2 different reagents, okay? And so we're so used to seeing an epoxide reacting with MCPBA to make the epoxide. Well, we got these extra things here. One more thing to add, okay? So these conditions don't form an enantioselective epoxidation unless the alkene, or the molecule that you want to form the epoxide, is a allylic alcohol. So there's our alkene. That's the allylic position. And attached to that allylic carbon is an alcohol. So you have to have an allylic alcohol, these 3 conditions right here, and then you are going to form one epoxide. You're not going to form enantiomers. So what you do, you just identify your alkene, okay? And I'm going to take the alkene and just draw carbon 1 and carbon 2. Okay, that's all I do. And then I draw my epoxide, connecting those 2. Right there. Now, we have this allylic carbon, which is attached to carbon 2. Okay, so we could say, hey, we have boom, like that, right? And then on carbon 1, we have 1, 2, 3. So 1, 2, 3. So I'm just getting the connectivity here. Now remember when we did the MCPBA with a simple alkene like this, and we did MCPBA. Remember when we formed the epoxide? Those are cis, so the stereochemistry stays cis in the epoxide. Remember that? Well, the same concept applies here. It's just now we have to just look at it a little differently. Here's our alkene. So we have the allylic carbon and then this carbon. Are they on the same side or opposite sides? They are on opposite sides of that alkene. So the stereochemistry is retained here. So we don't know if this positive DET is going to give us this guy. Turn that into a wedge. Right? But you see the stereochemistry is retained. They're on opposite sides, opposite sides. I do not know if this right here is going to give me this particular enantiomer. But I do know that whatever it gives me, it's going to be nearly 99. nearly 100%. Well, it's not that great. It's more like 98% selective. All right. So if I wanted this particular enantiomer, I have to do 2 experiments. I will do one experiment where I add the positive DET, and then I'll do a second experiment with the negative DET and see which one gives me the product that I desire. Okay, so you cannot predict what enantiomer you're going to get. But what is required is you need an allylic alcohol, these reagents, and you will get like nearly 100% of just one enantiomer. Okay, so that's a pretty cool reaction. Because just think how hard it is when you have an sp2 hybridized carbon, so it's flat. So the approach of the reagents have equal probability of attacking it, but not in an enantioselective epoxidation. These reagents right here select for one face of the alkene and one face only. That is very powerful. How much time do we have here? Okay. Okay, class, I think that's a good place to stop. And so next time we are going to take, after we synthesize an epoxide, we are now going to take that epoxide and do reactions with it. And that's a lot of fun. So, okay, so we'll talk about that in the next video.